this linear algebra approach gives us a really cool opportunity. And one of those opportunities is we can solve for using our kind of equation 98 that we saw in lecture 4. We can actually solve for a lot of unknown and stress values as long as we know the material, stress and strain values, excuse me, as long as we know the material and as long as we know, as long as we know the material and as long as we know some of the other values here. So I can write out, again, general form using engineering, stress and strain, the expression here. So basically I could relate my epsilon, and we can call this my S, compliance matrix. We'll learn a little bit more about that, and this. So here, this is a simplified form already. And you see, it's going to give us the equations that we had previously. So I know that epsilon 1,1 is equal to 1 over E times sigma 1,1 minus nu times sigma 2,2 plus sigma 3,3. That's just this in linear algebra form. It's epsilon 1 equals 1 over E times sigma 1,1, yep, minus nu over sigma 2,2 here, and everything else is 0. So we can take this approach, and then what about G? We saw in lecture 4, we go back, we had a definition for G is equal to E over 2, 1 plus nu. So let's go back. Excuse me for this, but it's important. So G is equal to E over 2, 1 plus nu. We also know that, again, if I know that gamma 1, 2 is equal to, or actually, excuse me, if epsilon 1, 2 is equal to gamma 1, 2 over 2, and I know if I write out my full form of epsilon 1, 2 related to stress, it's going to be equal to 1 over E times 1 plus nu times sigma 1, 2. So you can see here, we could actually write out the equivalence, right? So we know that G, if it's divided by G here, it gives us that 1 over, actually, excuse me, here. So you can see how actually you get the same exact expression. So if I plug in gamma, or use the G function, you see I can kind of get these equivalents right here. But we're not often going to use G effectively. Again, I would recommend stay within kind of your usual notation. So I'm going to write out, and actually let's go ahead, we could solve the problem that we ran into, our kind of complex stress state in lecture 4, this fun one, using kind of this other notation. So I could just replace basically my G with my 1 over nu divided by E. So just like we've done before. Again, Y and all those values. So let's define our stress state. So our stress full is equal to, let's go ahead, let's go over here. So remember, we did not know our sigma 1,1, we did not know sig 2,2, actually we knew sigma 1 was 0, excuse me. Sig 3,3 we did not know, and then the rest of them are all 0. So that's our stress full. We knew that our Y was equal to 100 times 10 to the 9th because it's a metal. We know our nu is equal to 0.3 because it's a metal. And once we have that, we have our full S tensor. So you could just say S matrix form. Oops. And you can kind of see the value. It would have been nicer to do that previously, but you can kind of see. Don't perform mathematical operations using this, but we've got that. So we can now basically solve for all the rest. So I could do, because I know S dot my, we could actually go back to here. We know that epsilon equals S dot our stress. So S dot stressful. It's not stressful at all to do these fun things. And you can see, let's look at this matrix form. I've got 1, 2, 3 equations. 3 equations, and I know, actually I could also solve that my strain full for that problem was what? I knew what? I didn't know what my E11 was. I knew that my E22 was 0, and I knew that my strain in the 3 was 0.5, and then everything else was 0. So I can go ahead, and I know that I'm going to get these functions. These 3 equations, I could set them equal, and I could just say solve strain full set equal to S dot stressful, and solve for basically E11, sig 22, sig 33, and voila, I got the values that we previously obtained for our other problem. Negative compression, positive strain here, they match if you look back and go through the video. So this is a cool way to solve quite a few problems. And again, I just want to bring your attention, this is equal to just what we wrote previously. It's just we're swapping out G with our definition basically here, and then we're using tensorial definition instead of this engineering one. So both you'll obtain the same answer. It's just, again, for convenience sake, I always like to I want to stay in the mindset of basically tensorial definition of stress and strain. But anyways, so now you can kind of see here. You could reduce notation if you're in a very lucky plane stress state, and then you could even, again, if you want to play around. You see, this is nasty, right? If we could actually do rotations as well, as long as you're in the plane stress state. But again, we don't want to mess with like look at all these R's and T. Just stay away from that. But this brings up an important point. How do we actually rotate a full 3D, basically tensor? Well, great question. So we will do that in the next video. So we'll see you then. Thanks. Bye.